recently I've been teaching a few classes on rotational mechanics, and then I see something very interesting about the moment of inertia. I see very few people realize what is the mathematical meaning of the formula I is equal to mr square, and how it can help you to feel the physics much better. So let's see. First of all, the moment of inertia is a scalar property. Right? It's not a vector property. So if it's a scalar property, you can add it very simply. And it depends on, you can see that it depends on the shape of the thing. It's depend where the axis is and all these things. But even in all of those, what it depends on is basically the mass distribution around the axis. So let's see that you have a two masses, and this is your axis. This red thing is your axis, and you have two masses, and combined together. So this is basically, I'm first explaining about what is scalar property. What do you mean by scalar property? So if you know the moment of inertia of this mass about this axis, which is because this is a point mass, so it's simply m1r1 square, right? And then of the second mass, that is m2r2 square. So the I total of this, both these things taken together, maybe it's not a rigid body, but you can take both of these things together, and maybe in some situation they behave like they behave very similar, and you have to take the moment of inertia of them collectively. Then if you have to take the collective moment of inertia of this system, then you can simply add it. You don't have to go into vector sum. This is a scalar property, so that's a very good news. This is a very simple property, just like in electrostatics. When you have a potential, it is very easy to work with potentials than with fields. Anyways, so what matters here is the square mass distribution. By mass distribution, what do I mean is that what matters is the square of the perpendicular distance of masses from the axis. Because very simply, I is mr square. The most basic definition, I is of a point mass if it's at the distance r from the axis, perpendicular distance of course, from the axis, then the I is mr square. Okay, so this mass here, you see this mass here, and this is the axis, and this mass is m, and let's say that the distance is perpendicular distance is r, and then the moment of inertia, you will see that this is mr square simply. But if you change it into a ring, a circular ring, you see the whole mass, the mass hasn't changed. The mass is same as before. You have just changed the geometry, but still the mass, all the mass is at perpendicular distance r from the axis. So your moment of inertia hasn't changed. It's still mr square. And if you turn it into, let's say this point mass, if you turn it into a straight line parallel to this axis at a distance r, then again you haven't changed the perpendicular distance of the mass from the axis, and all the mass is still at the distance r from the axis. That's why the moment of inertia is mr square. And you can also transform it in a cylinder. Both things combined, like you turned it into a ring, and you also turned it into a rod at the same time, parallel to the axis, and what you get is a cylinder. And now also you see that somewhere here also, this point also, this axis is going from I can't show the axis here, but you can feel that this point also is at a distance r from the axis. So all the mass is still at a distance r from the axis, and the moment of inertia is still mr square. This distribution, if you feel, then you can very easily figure out what are the moment of inertias. Even if you don't figure out exactly, then you have a qualitative idea. So it's not always about the quantitative exact formula. You need to have some qualitative ideas also while doing physics. Okay, so let's see that we discussed that these four moment of inertias, all of them are mr square, because the mass distribution is same. All mass is at a perpendicular distance r from the axis, perpendicular distance, right? So notice that also. Then let's think about the sphere. Just to clarify some things about mass distribution, the axis is not a point, first of all. this is a thin spherical shell, okay, shell. This is a thin spherical shell, so all the mass is at the periphery only, not inside. Inside there is nothing, okay. So the axis is not a point, but it's a line. So now if you feel like the axis is like a point, it is not, then if you thought like a point, the axis was like a point, then you would say that all the distance is all the mass is at a distance r. But the axis is a line, and now you can see that all the distance is not at a distance r. Most of the mass is closer than a distance r to the axis, isn't it? Because this distance from the radius of this shell is these distances, and these distances are different. So then you can feel that because of the change in geometry, all mass is at a distance r from the center, but the center is not the axis. All mass is not at a perpendicular distance r from the axis. In fact, most mass is at a perpendicular distance less than r from the axis. And if you do the scalar sum, then you would realize that I will be less than mr square, right? How much it is, then you can calculate it using calculus, but you have to feel it first that the I is less than mr square. Okay, so I will talk about this rod also. So in this rod, this is the axis, it has a mass m and it has a length L. So all mass you can see is closer than a distance L by 2, because this is the farthest mass from the axis and it is at a distance L by 2. So if even if like all the mass was at L by 2 distance, then you will get the moment of inertia ml by 2 whole squared. But this time the moment of inertia will be less than ml square by 2, isn't it? It would be less than ml square by 4, which means. And here I can show you a little bit of calculus to prove it that this assumption is right. This thought is right. So how do you do the calculus? So you have a small element here at a distance x from the axis, and its width is tx. Then the mass element here, because the whole length L has a mass m, so unit length will have a mass m by L, and dx length will have this mass, right? And using this mass, the di, the small moment of inertia, the moment of inertia of this small part will be its mass time its perpendicular distance from the axis. So m dx by x square, and there is no vector I cap or j cap, nothing like that. You just have to integrate it or sum it to get the final moment of inertia, and the integration runs from minus L by 2 to L by 2, because this x, if you take go to minus L by 2, you have you start from here, and then from here to the whole rod till L by 2 plus positive L by 2, you cover the whole rod, and then you sum it using integration, and what you figure out that the moment of inertia is ml square by 2L, which is much less than ml square by 4, right, as we suspected. Anyway, so now the insane tricks. So suppose you have a rod. So I haven't seen these tricks before, I think, in my life. So I was very excited when I saw this. So let's see. This is the rod, and the moment of inertia for the rod is ml square by 12. So what happens if I make a rectangular plate? I turn this mass. Suppose this I hit this mass with a hammer and turn it into a sheet like this. So now I have a rectangular plate of mass m and length L and breadth b. And notice that I haven't changed the mass distribution, because all the mass which was here has now spread out into this part, and the perpendicular distance of this mass element is same as before. So for all the mass elements, distance, the perpendicular distance from axis hasn't changed. That's why this should be. And even for the square plate, even if you hit it more and you spread it more, you are not changing the mass distribution. I mean, you are changing the mass distribution, but not in a way that the square of the perpendicular distance of the mass is changing. That's why all of these things will have moment of inertia. ml square by 12, okay, about the axis which is shown here. So for the rod, it's ml square by 12. Then for this rectangular plate, it should be ml square by 12. Then for the square plate also, this will be ml square by 12 about this axis shown here, pink line. Okay, and then suppose if you have to find out the moment of inertia of a rectangular plate about this point, then what would you do? Then you can use, there are two very useful theorems in moment of inertia. When we discuss moment of inertia, I will maybe go into their proofs in some other video, but now you can see that about this axis, it's the same as like mb square by 12, because about that axis we discussed it was ml square by 12, right? So now if you use the perpendicular axis theorem, then you will see that the moment of inertia is ml square plus b square by 12. Okay, and then now taking this moment of inertia, and from here you can think about the cubes and the cuboids. So if you make a cuboid, and the cuboid is like this sheet, and you extend the sheet, into a cuboid, and you see you can take any mass. Suppose this point mass here, this point mass has become now a rod, and this point mass was at some distance, let's say x. This whole rod is now at that distance x, isn't it? So using the scalar sum of these small elements and the same distance here, if you figure out of this element only, the moment of inertia will be dmx square, as before this element here also has dmx square. And if you apply the integration, and you will have the same limits, and you will end up with the same formula. So basically the mass distribution has not changed. The mass distribution which affects the moment of inertia has not changed. Yes. So similarly, if you talk about this axis, so now you can draw similarities, that if the axis was passing through the face of with lengths L and B, and now this axis is passing through the face with lengths B and H. So about this axis, it would be mh square plus b square by 13. And then you can't use the perpendicular axis theorem here, because this is a 3D object, and I will not go into that, but you can figure out about this axis, and maybe also this axis you can figure out separately, drawing the similarity. This axis is about the lengths L and H, and using the same similarity, m will be L square plus H square by 12. Okay, so if you understood what happened here, then you can think about this question. This is very interesting. So I would like to see what do you think about this question? Arrange the moment of inertia of the following uniform solids. These are uniform solids. They are not hollow solids. They are uniform. They are solid. They are not hollow. And their mass is m, but their geometries are something like this. Okay, so take a look at this for a while and think what would be the answer. There's nothing tricky about it. It's very fundamental. Thank you for watching.